In this video, we are going to learn Burnside lemma. This is a very useful tool to compute the number of orbits. So the goal today, our goal today is to find the formula for the number of orbits when we have a group action. So suppose that G is a group acts on X, set X. And let me define two things which will be used for group element G. Let fix of G is the set of all elements in X that is fixed by this action G. That means G bar of X, G bar X equals X. And similarly, for now fixed noun elements in X, let fix of X to be the set of group elements which fixes that that element in X. Okay. Now we need a lemma before stating or proving the Burnside lemma. We need to prove one algebraic lemma for any X. We have this property: the size of the group is equal to the size of the orbit times the size of the number of elements in the group that fix the element X. Alright, so let me prove this lemma. So we have given X, so let the group, the orbit has k elements, x2 dot 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 xk. Here on orbit, the orbit of X always contains X. So we particularly say that x1 is X, okay? Because the orbit always contains X. Then for any group element G, if we apply G to X, it will be one of these elements in the orbit, because that's the definition of the orbit. We have this for some I. So let G sub I be the set of group elements which sends X to Xi, where I is from 1 to up to K. Then of course the whole group G will be partitioned into this group. These may not be groups. These are subsets. The group can be partitioned into subsets like this. And what is G1 in particular? In particular, in this definition, look, G1 is equal to fix of X, because G1 is a set of group elements which sends X to X1, but X1 is equal to X, so it fixes X. Okay, so we know that this group is partitioned into subsets like this. So our claim is that, let me write this. Claim is that each group, each subset Gi has the same cardinality as the fix of X. Of course, it's obvious when I equals 1, because fix of X is equal to G1, but the cardinality are the same for all Gi. So let me prove this claim. it is enough to find bijection between the two sets. Say phi from fix of x to gi. We will construct a bijection. For that, take an element, say h, in gi. That means then what happens is if we apply h to this set at element x, then we will get xi, because that's the definition of g sub I. And now we define the function phi from fix x to gi by multiplying h. Phi of g is equal to hg. So this is group operation, gh. Then first we need to show that it is in fact in the range gi. Phi of g, in order to check, we need to check that this is indeed gi, because hg bar is the gi, phi of gi. If you apply g, then because it's a group action, we have this, which is h g bar of x, but because g bar came from fix, so let me say for g we have g bar in g. We have phi of g is in gi. Here, because g bar fixes x, we have h bar of x, and we have taken h bar to be in g, so this is going to be xi. So we know that phi of g must be in g, right? And then phi has the inverse, phi defined by, say, so it h inverse g. You can check that this is the inverse, because phi, say, compose phi inverse of any element g, phi inverse phi of g. Phi of g is defined to be hg, and this phi inverse, the definition is, and because of the associativity, we get g. Similarly, you can check that this is equal to, you can do the same thing with this. So it is the inverse, and because the function has the inverse, it's going to be a bijection. So this is a proof of the claim. Now, by the claim, we know that because g is the cardinality of the size of g is plus g1 plus g2 plus dot 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 gk, but by the claim, every gi has the same cardinality as fix, so it's equal to fix of x times k. But k is the cardinality of the orbit, which is the size of the orbit, of course, so it's going to be size of the orbit times fix of x. This is a proof of this lemma. Alright, using this lemma, now we are going to prove Burnside theorem. So theorem, and is called Burnside lemma. The statement is the following: g acts on x, then the number of orbits is equal to 1 over G summation G in G cardinality of cardinality of the element fixed by G. So proof. Alright, the idea is to compute the number of pairs. Let's compute number of pairs G comma X such that G fixes X. Let's compute these pairs. We compute these pairs in two different ways. First, we fix G and then compute the number of elements fixed by each G. Then it's of course this. But on the other hand, we can also fix element X first and then compute the number of group elements that fixes X. Okay? But here, by lemma, by the previous lemma, if you use the lemma, this is equal to X in X. The lemma here states that group element G, number of group elements is equal to the size of the orbit times size of fix of X. So fix of X will be equal to the group element over the size of the orbit containing X. Okay? Now here, if you divide both sides, this and this, by G bar, cardinality of G, we get 1 over G in G fix of G is equal to summation X in X 1 over Gx. Alright, now we sum over all X in the set X, and because we know that X is partitioned into orbits, Gx1, okay, maybe it's like that. Say O1, O2, say, or say M. So M is the number of orbits. We know that orbits form a partition of X, so we have this. And actually M is the number that we want to count, number of orbits. And here, okay, so this part can be rewritten using orbits. I is from 1 to M, X in the orbit 1 over Gx. Okay, but what is Gx? If X is in orbit I, that means G of X, the orbit is the ith orbit. So this means I is from 1 to M, X orbit, oh, I made a mistake here. It should be I 1 over orbit I. So if you look at this sum, for every element we add the in 1 over the size of that orbit. That means the contribution for this will be 1. This is always 1 because we add, if there are like 3 elements, we add 1/3 for each element that will give us 1. So if for every group or every orbit we add 1, that means this is equal to the number of orbits, which is M. That's the proof of this lemma. Okay. Alright, now let me show you how to use this Burnside lemma to count the number of orbits. I'm gonna just show you a very simple example. Rotation group of square 1, 2, 3, 4, and that will be we will say identity rotation 90 degree rotation 180, 270. There are 4 elements in this rotation group, and X is, let's say, colorings of the vertices, 4 vertices of this square with 2 blacks, 2 whites. And we know the number of orbits is 2 equals 2 because there are 2. We can list them all. There are B, B, W, W, and these are 2. There are only 2 orbits represented by these 2. Any 2 colorings can be obtained from one of these by applying the rotations. But let's compute this using Burnside's lemma. We will check this using the lemma. Number of orbits is equal to 1 over cardinality of G. Let me just write this. Or R, because we are saying R is the group. G is in R, 1 over, oh, this should be R. What am I doing? So G fix the number of elements fixed by G. Okay, so let's write this. So the cardinality is 4, so 1 over 4, and we want to compute fix of identity element, fix of rotation rho, cardinality of the fix rotation squared, fix rotation cubed. Alright, so let's compute this. So what is this? Number of elements fixed by identity element, identity rotation. If it doesn't do anything, it will be, of course, fixed. So it's the all elements in X. And there are, so let me list all of them just for clarity. So there are 6 elements. All of them will be fixed. So it is going to be fixed. Then the number of elements fixed by rotation. If you do this rotation 90 degree, nothing will be fixed. So it's going to be 0. If you rotate 180 degree, these are not fixed, but this will be fixed. This will be fixed. So there are 2 elements here. And if you rotate 270 degree, nothing is fixed. So the sum is this, and then this is going to be equal to 2. So this is, of course, equal to the number of orbits. So in this example, it's very simple, so it's easier not to use Burnside lemma, but if the problem is more complicated, then Burnside lemma can be very, very useful. And the reason why Burnside lemma is useful is that usually, or many cases, in many cases, fix of G is easier to compute. This means number of configurations fixed by this group element G. This is easier to compute. So if you look at this, Burnside lemma, if you can compute fix of G for every G, you can get the formula. And many cases, this is easy to compute. So that's the benefit of Burnside lemma. Okay. Okay, this is the end of the video. Thank you very much for the watch.